Morning, everyone. Good morning, Dr. Nelly Freudiariyama, as the head of the Education and Training Center of BMKG. Assalamualaikum warahmatullahi wabarakatuh. So,
Waalaikumsalam.
in this time, welcome to the Regional Focus Group Meeting or RFG May 2024 and BMKG Online Group Discussion 217. Respectable, the head of Education and Training Center of BMKG, Dr. Nelly Flauderiyama, the Honorable all speakers of this meeting, also welcome Dr. Buddha Siki from the Australian Bureau of Meteorology, BOM, and the Honorable all participants and other colleagues. In here, I'm Hafid Rizky Pratama, and I will be the moderator of meeting today. So I'm very pleased to see you here and welcome all of you to this meeting. First, for beginning this meeting, there are some opening remarks from Dr. Nelly Fleuderiyama as the head of the Education and Training Center. Dr. Nelly Fleuderiyama, please, time is yours.
Thank you, Kafid. Good morning, good afternoon, good evening, everyone. So thank you very much for joining us today. And I want to welcome you all to this Joint Indonesia BOM Virtual Laboratory Center of Excellence for Education and Training in Satellite Meteorology Regional Focus Group meeting. I notice here we have many participants also, not just from Indonesia, but also from Australia, Myanmar, Samoa, Solomon Island, Korea, Japan, USA, and also Hong Kong. Thank you very much for joining us. So this meeting today is as already mentioned by Kavit, is a regional focus group meeting and also serve as our BMKG online group discussion. And this is dual significant highlights the importance of our gathering and continuous effort we make to advance our knowledge and skills, especially in satellite meteorology. We have our speaker today. We have Bodo and colleagues from BMKG, and and also it is our if I'm not mistaken, it is our third, yeah, Bu Ani.
Yes, it's our third of 2024 for
G. So yeah, we have started since this January. So yeah, I would like to also thank you to all the speakers, including from BMKG. We have Muhammad Hanif Afan, and then we have Richard, and also Faradi Diva, and of course Bodo from BOM. So talking about the topics, we also noticed that recently we have seen the crucial role of satellite meteorology, especially in aviation safety. We still remember the turbulence incident involving Singapore Airlines and also Qatar Airways. So I think this is need to underscore how the need for advanced satellite data to predict and manage turbulence. And also, we also want to hear from other speakers on specific issue on the tropical cyclone, on also how the use of this satellite for aviation weather service, and also the ocean surface response during the TC from the satellite data. So I do hope that our event today's will give us more and more insight or new knowledge from us, and I hope that we can engage in fruitful and productive discussion. So let us use this opportunity to enhance our understanding and capabilities in satellite meteorology, that driving forward the quality of our weather services. Thank you all, Thank you all, and I look forward to our successful RFG meeting today. Thank you very much.
Thank you very much for Dr. Nelly Floridiarama for the opening remarks for meeting today. So before we begin, I would like to introduce you this presenters. Our presenters for today are from the division in Meteorology Deputy, Muhammad Hanif Afan from the Public Meteorology, Faradifa from Maritime Meteorology, and Richard Mahendra Putra from the Aviation Meteorology. Today, they will present about the satellite meteorology to support operation. So the satellite meteorology plays crucial roles in the modern weather forecasting and climate studies. Its application for the operational purpose encompasses a wide range of activities that help in weather monitoring, weather predicting, or numerical weather prediction, and mitigating the effects of weather and climate. Before the presentations begins, let me inform you all, if you want to ask questions, please typing in the chat box during the presentation or raise your hand after the presentation. We have the limited question each speaker about 2 questions because the limited time today. Well, we start to first presentations by Mohammed Hanif Afan from Public Meteorological Center. Mr. Hanif working as expert on satellite meteorology in this division. He will present about the monitoring of the tropical cyclone in Indonesia using satellite. We allow 15 minutes for its presentation. Mr. Hanif, time is yours.
Thank you, Mr. Hafid. So good morning, ladies and gentlemen. I would like to greet Miss Nelly, Miss Annie, and Mr. Bodo, and Mr. Richard, and other participants. So today, I would like to share with you all about monitoring of tropical cyclone in Indonesia using satellite. I would like to share my screen. I hope my voice is clear enough. Is it?
Yes.
Okay. Can you see my screen now?
Yeah, of course.
Okay, so before I start, I would like to introduce myself. My name is Muhammad Hanif Afan Yusron, but you can call me Hanif. Currently, I'm working in the BMKG, Indonesia's Agency for Meteorology, Climatology, and Geophysics, specifically in the Center for Public Weather Services. I work since 2019 in BMKG. Let's move on to the outline. So there are 4 points that I would like to share to you. The first one is prevalence of tropical cyclone in Indonesia. The second, why do we monitor tropical cyclone in Indonesia? The third, the most content is identification of tropical cyclone in Indonesia using satellite. And then the last one will be case studies of tropical cyclone in and near Indonesia. Okay, so speaking of prevalence of tropical cyclone in Indonesia, we have to speak first about the location of Indonesia. Indonesia is located near equator, from the latitude of 6 degrees north until 11 degrees south, and then longitude of 95 degrees east until 141 degrees east. Because of the location near the equator, Coriolis force in Indonesia is minimal. Hence, tropical cyclone formation in Indonesia is limited. As you can see in the right image, this map shows the tracks of all tropical cyclones from 1985 to 2005. We can see clearly that the track of tropical cyclone in Indonesia is minimal, but in the southern and northern edge of Indonesia, there are plenty of it, specifically in the Indian Ocean and Pacific Ocean. Even so, historically, tropical cyclones near Indonesia happen frequently every year. Move on to the next slide. So why do we monitor tropical cyclone in Indonesia? Because obviously tropical cyclones in and near Indonesia bring significant impacts to several areas. The impacts include heavy to extreme rainfall. The second one is strong wind. And then the third one is high sea waves, especially the tropical cyclones not making landfall to Indonesia. So how to identify tropical cyclone in Indonesia? One of the most popular instrument for monitoring and identifying it using remote sensing is satellite. So there are two types of satellites for monitoring the tropical cyclones. The first one is polar satellite. The second one is geostationary satellite. So basically, polar satellite is a satellite which has a low orbit altitude around 100 kilometers above the Earth's surface, while geostationary lies very high, about 36,000 kilometers above Earth's surface. Because of that location of the satellite, we can see that polar satellite has a higher spatial resolution because of the location, but at the same time, it has lower temporal resolution. It only passes a location twice a day. And because of the nature of the polar satellite, it will give us blank zone while monitoring the Earth surface, including the tropical cyclone. As we can see here in the left image, we can see this is Cyclone Seroja, which was happened in 2021 in East Nusa Tenggara Province in southern part of Indonesia. We can see that there's a blank zone, a black here, which make the monitoring is not better than the geostationary satellite. While the geostationary satellite, since the altitude is very high from the Earth's surface, it can stay above certain location without moving anywhere. So it can bring us higher temporal resolution, up to 10 minutes. So we can retrieve an image from this geostationary satellite, 10 minutes each one. And then we will have no blank zone. So we can see clearly the Cyclone Seroja here. But since the location is very high up there, geostationary satellite have lower spatial resolution, about 2 kilometers, but it is actually still acceptable since the size of tropical cyclone is quite big, in order of 100 to 1,000 of kilometers. So in Indonesia, we use 3 geostationary satellites for monitoring the tropical cyclone. The first one, and it's currently operational, is Himawari 9 satellite from Japan Meteorological Agency. The second one is Geocomsat 2A, which is recently adopted in BMKG since 2022 from Korea Meteorological Agency. Korea Meteorological Administration. And then the third one is Fengyun 4B satellite by China Meteorological Administration. But unfortunately, since there's some hardware issue, we haven't retrieved any more Fengyun satellite image. So what is the satellite role for tropical cyclone monitoring? There are 3 roles basically that many of us know. The first one is monitoring the tropical cyclone position and track the position in real time. We can see whether the tropical cyclone moves north, south, east, or west. We can see it by satellite. And then the second role is estimating tropical cyclone intensity and size by several methods. And then the third one, we can improve tropical cyclone forecast by assimilating the satellite data into numerical weather prediction model. So by assimilating the satellite data, which observe the tropical cyclone, we can improve the accuracy of the tropical cyclone forecast. In BMKG, we have 4 products here, which are used for monitoring the tropical cyclone. The first one, the most popular one, is enhanced infrared image. This image is retrieved from band 13, both from Himawari 9 satellite and Geocomsat 2A satellite. And then the second one is sandwich product. This image is basically similar to enhanced infrared, but we developed several color scheme to highlight the significant convective cloud from the tropical cyclone. And then the third one is rainfall potential. This product estimate the total rainfall every 10 minutes from the band 13 of satellite image. And then the last one is gas map rainfall image. We have the data in the image every hour and daily. So as you can see here, the red one belongs to very heavy rainfall. The yellow one is heavy rainfall, which is the one that we pay attention more in terms of tropical cyclone monitoring. Next method is a very important one, which is Dvorak technique for estimating the intensity of tropical cyclone. So besides aircraft reconnaissance, we can also estimate the intensity or the maximum wind speed of tropical cyclone by actually looking at the shape of tropical cyclone using the Dvorak technique. So the Dvorak technique is first developed in 1980s by Dvorak himself, and then this method developed time by time. After the first edition of the Dvorak technique, it developed into digital Dvorak in late 1980s to 1990s. And then it developed again into objective Dvorak technique. And then after that, it is developed into AODT, Advanced Objective Dvorak Technique. And then starts from 2004, Advanced Dvorak Technique. But after Advanced Dvorak Technique, there was actually recent research which implement the machine learning model into Advanced Dvorak Technique. So it will result in better performance of the Dvorak technique itself. So for your information, the early of Dvorak technique can estimate the intensity of tropical cyclone with the root mean square error about 10 to 15 knots of wind speed. While the recent one, the AIDT, Advanced Dvorak technique with machine learning model implemented into it, can result in the root mean square error of maximum wind speed about 8 knots. So it definitely is better performance. So in the Dvorak technique, we can estimate the intensity by looking at the shape of the tropical cyclone or tropical cyclone seed. By example, we can see that the left image is obviously different from the right image. So we can see there are several T numbers here, T1.5, T.2. So it belongs to several intensity categories. The lower the T number, the lower the intensity of tropical cyclone. In Indonesia, if we use the Dvorak technique and we identified that the T number is between 1 and 2, the object will be categorized as tropical cyclone seed or bibit cyclone tropis in Indonesia.
And
While if
the minutes left.
okay, while if the T number is more than 2, it will be categorized as tropical cyclone. But in around United States of America, we can see plenty of tropical cyclone with more than 2, the T number. For example, there are tropical storm Wilma, tropical storm Dennis, Hurricane Jan, and Hurricane Emily. Each of these T number is represented by certain characteristic of shape in terms of cloudiness from the tropical cyclone. There are other research of tropical cyclone identification using satellite. The first one is Deep Tracy, which is about life stage identification of satellite tropical cyclone image. So this research focused on life stage identification from tropical cyclone seed into tropical cyclone, etc. This research is conducted by H. Sakaino in 2023. And then the second one is tropical cyclone size identification over the Western North Pacific using support vector machine and general regression neural network, conducted by Lu et al. 2022. Now let's move on the case studies of tropical cyclones in and near Indonesia. The first one, and one of the most significant tropical cyclone which has ever impacted to Indonesia, was tropical cyclone Cempaka, which was happened in November 2017. This tropical cyclone impacted the island of Java and Bali, especially the southern part of Java. And Although this tropical cyclone didn't make landfall, Cempaka managed to cause 41 deaths, more than 20,000 people evacuated, and causing around 83.6 million US dollar in damage. So it is significant in terms of impact. The highest wind recorded from Cempaka was 110 kilometers per hour. And then the highest rainfall recorded from Cempaka was 383 millimeters, which is considered extreme rainfall here in Indonesia. This rainfall is recorded in Pacitan, East Java. And this tropical cyclone also caused severe flooding and landslides across 28 regencies and cities in Java. I'm afraid the the right image supposed to be animation of tropical cyclone Cempaka, but unfortunately it seems doesn't working. So I will show you later if it's possible. Yeah, now works. This is the animation of tropical cyclone Cempaka. It moves right at the southern coast of central and eastern part of Java. And then tropical cyclone Cempaka moves around here, southern of Java with this track. And then from gas map 24-hour rainfall accumulation, we can see that there was heavy to extreme rainfall in southern part of Java, specifically in Central Java, Yogyakarta, and East Java. And then obviously the Cempaka results in flooding and landslides. Now let's move on to the second case study, which is tropical cyclone Seroja, which was happened in April 2021, in East Nusa Tenggara, which is southern part of Indonesia. In Indonesia itself, Seroja caused 183 deaths, destroyed more than 20,000 houses and 5 bridges, also more than 12,000 people evacuated. In Indonesia, highest wind recorded from Seroja was 100 km per hour, and rainfall recorded from Seroja was 159.7 millimeter, recorded in our island in East Nusa Tenggara. Like Cempaka, Seroja also caused historic flooding and landslides. This is the track of Seroja. It starts in East Nusa Tenggara and then moves to the southwest to the western sides of Australia. And then this is the gas map 24-hour rainfall accumulation. We can see here that obviously there are huge areas which was impacted by heavy to extreme rainfall from Seroja. And then this one is damaged road caused by tropical cyclone Seroja. I would like to also give you a third case study, which is Typhoon Sergei, happened in 2021. Typhoon Sergei happened north of Indonesia, east of Philippines. So it starts from east of the Philippines and then moved to the west across the Philippines. Even though it didn't make landfall in Indonesia, it creates rainfall band, as we can see here. Rainfall band affected northern part of Indonesia, such as North Maluku. We can see here from the gas map rainfall image, there was moderate to heavy
Mr.
rainfall.
Hanif, time is
Okay.
over. Can you skip to the summary?
Okay, so that's it from me. Thank you for the time and for the opportunity. Mr. Rafid, back to you.
Thank you very much, Mr. Hanif Afan. So, the questions in the end of the presentation. So we will move to the next presentations by Mr. Richard Mahendra Putra from Aviation Meteorological Center. So Mr. Richard have experience on the satellite imagery, especially artificial intelligence for volcanic ash. Today, he will bring the presentations about the role of weather satellites for aviation weather services in Indonesia. So, Mr. Richards, you have 5 minutes for presentations. Mr. Richards, time is yours.
Okay, thank you, Mr. Moderator. Can you hear my voice?
Yes.
Yes.
Okay, thanks. Okay, the Honorable Head of Education Center BMKG, the Honorable Mr. Bodo from BOM, and all speaker, and also all the participants in this discussion. And this is my first time to be the speaker in PhilLab, and I'm very glad to be here. And in this section, we will discuss about the role of weather satellite for aviation weather service in Indonesia. First of all, let me introduce myself. My name is Richard. I'm meteorologist in Aviation Weather Center, BMKG, Indonesia. This is the content of presentation. We will start with the introduction and then the role of weather in aviation, because it is important. And then I will show you how the profile of aviation weather service in Indonesia. And we will see the role of satellite for aviation weather service in Indonesia. And I will show you one of example, the research with using weather satellite for aviation. And the last is about the conclusion. Okay, next. This is introduction. Like Mr. Hanif said, that Indonesia is located in the near the equator, and the Indonesia is located between the largest ocean in the world, the Pacific Ocean and the Indian Ocean. And because of that, the weather prediction and forecasting in Indonesia is not easy. It is because of very complex. For example, like this. In Indonesia, we have a lot of global factors that have important roles for the weather and climate condition in Indonesia. For example, ENSO, and then IOD, and then monsoon, and also Indonesia is impacted by Madden-Julian oscillation. And we have to know that the weather condition have a various impact on the flight safety. For example, aviation flight hazard is a thunderstorm. It is very dangerous for the aircraft. This is the example that the aircraft is avoiding the thunderstorm in some cases. So when the condition of thunderstorm is occur, the aircraft have to avoid that. And beside that, the aviation hazard is also the icing and then turbulence and then the volcanic ash. Maybe turbulence will be discussed with Mr. Bodo. And then the volcanic ash, for your information, in the Indonesia, it is the ring of fire. So it's have a lot of volcano active and it can erupt every time. And also we use the satellite to give the information of volcanic ash distribution. We will discuss it later. This is the aviation weather service profile in Indonesia. And the first, we give the information about weather observation. This is important for takeoff and landing of aircraft. It is METAR and spaceship. And then the weather forecast. So not only the observation we give to our stakeholder, but also we give also the weather forecast. For example, in the aerodrome, TAF, and then we also give the significant weather and route of the aircraft movement. And besides that, we also give the issued with weather warning when the weather condition is dangerous for the aviation sector. For example, it is severe thunderstorm and tropical cyclone, volcanic ash, and then wind shear condition. And beside that, we also give the information of aviation weather service using flight documentation. This is the document that consists of weather observation, weather forecasting for the airport, temperature, destination, and alternate. And then also we give the information about significant weather chart, wind time chart, weather radar, and weather satellite. So this is all our information to give to the stockholder. This is the example. This is example of observation. This is the chart example for the forecast. And then this is example for warning. And this is our division structure in Aviation Weather Center in BMKG. We have 4 divisions: division for service, division for observation, division for operation, and then division for administration. And beside that, we also have a meteorological station in the airport in Indonesia. So the meteorological station have a duty to give the direct information of weather condition to support the aviation sector in that area. So for example, like METAR, SPECI, TAF, aerodrome warning, wind shear warning, SIGMET, flight document, and weather briefing. And this is the This is the challenge. Sorry. This is the challenge of Indonesia. Like Indonesia is a big country. So many airports in Indonesia, and not all the airports have meteorological station, but we provide the weather observation instrument to that airport, so it still can give the information of weather condition. And beside that, we also give the training to our stakeholders to use the operator and then to know how the weather condition in that area. So this is the challenge of Indonesia. And the next, this is our equipment that's to support the information of aviation weather service. We have a AWOS, automatic weather observing system. We have LiDAR for wind shear. We have low-level wind shear alert system. We have radar for wind shear. We have a balloon of radio sonde, and also we have wind profiler data to give the support information. This is how we disseminate the information of weather service in Indonesia. We disseminate by one website, and then we also disseminate by the interactive platform. It's called SIAM, System of Indonesia Aviation Meteorology. And also we give the information of our weather service for aviation using mobile application Info BMKG. If we see in the website, we see a lot of information in that place. For example, we can see the observation, we can see the SQT for radio sonde, upper air observation. We also provide the stakeholder by the WFC.London data visualization of cloud-based height, clear air turbulence, icing severity, eddy dissipation parameter, and then wind chance chart. And if we use the platform, the interactive platform, it's called SIAM, we can see the real-time display of weather observed information for aviation. So this is the real-time, and this is interactive, so we can zoom out, zoom in, we can find where is the place that we want to see in the aviation weather condition. And in this system, in this platform, we also give the automatic flight documentation for pilot and airline. So using this platform, we can give the automatic flight documentation. And we also give the information by using the mobile application. And this is the role of satellite for aviation weather service. Like we discussed before, that our service for information of meteorological is about observation, forecasting, and warning, and also flight document. And we also give the report when the aircraft incident is occur. And all of this information, if we need the satellite to support. So the weather satellite have an important role to support weather observer and weather forecaster. This is the example for observation in METAR, for example. METAR is the routine meteorological aerodrome report. It have some kind.
You have 1
Yes.
minute left.
Okay. It is a cloud cover. So when cloud cover, it is using METAR, we have to cloud type for satellite. And then for TAF, it's also, and then for warning, we also need the satellite information. And then for flight document, it is one consists of satellite information. And then for aircraft incident, it's also need the satellite. So this is only in sample for the research of volcanic ash using satellite, using by machine learning. And this is the result I will show you. When we see the machine learning to give the satellite for volcanic ash, it is have same pattern. So this is the result of the discussion. And the last is about conclusion. So we can see that weather information is important for aviation safety, and weather satellite have a very important role to support the weather observation, to support weather forecasting and weather warning, and also will be used for flight document and report of aircraft incident. And we have great opportunity to develop the satellite technology for research for aviation, especially for aviation hazard that have a significant impact on aviation sector. Okay, I think that's enough. Thank you for the time. And if you have the discussion, let me know. Thank you.
Thank you very much for the presentation of Mr. Richard Mahendra Putra. So we will move the next presentation from Bu Farah. She will bring the title of Ocean Surface Response during the process of the tropical cyclone in Indonesia. So you have 5 minutes for presentations. Please, Bu Farah, time is yours.
Yeah, thank you. Let me share screen first. Yeah. Can you see the share screen?
Yes.
Okay. Hello everyone, I'm Farah. Today I'm gonna ask you to imagine first. Imagine standing on a serene beach, the sun shining brightly and the waves gently lapping at the shore, and suddenly dark clouds gather on the horizon, and within hours, the scene transforms into a chaotic battle of wind, rain, and surging waves. And this dramatic transformation is the result of a powerful tropical cyclone, which is a force of nature that not only affects the land but also the vast ocean surface. So today we will explore how satellite data helps us detect and understand these formidable processes over the ocean surface, specifically focusing on tropical cyclones in Indonesia. So this is the outline. We have background, objectives, and structure. Next, as the previous speaker explained that about the Indonesian region and so on, so I'm gonna skip that because it's already explained. And this one as well, how the tropical storm forms, because X explains by the previous speaker regarding the formation process of tropical cyclone. I won't reiterate it. And next, this is the cyclone effects on the marine and coastal environment. So we know that cyclones have profound and often devastating the effects on marine and coastal environments. When a cyclone makes landfall, its powerful winds and heavy rains can cause several coastal erosion, reshaping shorelines and altering the habitats of numerous species. And the storm surge that accompany cyclones lead to increased sea level, inundating coastal areas with weather, which can damage or destroy vegetation and disrupt local ecosystem. So for satellite data, using ocean parameters observed by satellite data in terms of detecting for tropical cyclones, we have low-level Earth satellite observation. Well, actually, the first satellite observation of SST began in the 1970s using IR radiometers on board the NOAA, geostationary and polar orbiting satellites. And we have some methods. The first satellite-based synthetic aperture radars, or SAR, for tropical cyclone monitoring. It has high-resolution observation, provides images with below 100-meter resolution, uses C-band and micro-radar pulses, and it has also advantages, sensitive in high wind and rain condition. And current mission is Sentinel-1 from ESA and RadarSat-2 from Canada. And collaboration with NOAA and IFMR support GTWC and NHC forecaster. And we also have method like multi-satellite cyclone for detection. We can combine the optical satellite, the synthetic aperture radars, and satellite plus in situ observation in terms of detecting tropical cyclones using ocean parameters. So if we talk about satellite data observed of ocean parameters, we need to highlight some of the things. The first, the temporal resolution depends on the orbit parameters and sensor parameters. And the second, spatial resolution is different for each sensors. Microwave sensors are spectrometers, altimeters, radiometers, SAR, And over the ocean, they aims at providing information on ocean surface wave, temperature, rain, and currents. And we can see the ocean parameters in terms for detecting tropical cyclones. There are sea surface temperature, sea surface wind, and chlorophyll A concentration. If we talk about sea surface temperature, why it can be detected for tropical cyclone. The SST is an important factor in the supply of energy to tropical cyclones and affects not only their formation but also their track and intensity. Even if other atmospheric conditions are favorable for the development of TC, it will be difficult for TC to develop if the SST is low, and no storm will develop at an SST below 26 degrees Celsius. So the two pictures illustrate an important observation. Before the tropical cyclone forms, the SST in the area where the cyclone develops is above 26 degrees Celsius. So this elevated temperature is a critical factor in the formation and intensification of tropical cyclones, as the warm water provides the necessary energy to fuel the storm. And sea surface wind, we know that the SST gradient over the marine region generates the pressure gradient in the boundary layer. It drives the horizontal winds over the ocean surface. The higher the SST gradient, the higher is the surface wind speed. And yeah, ocean winds can drive ocean currents and surface waves. We can see the picture of in the left side is depicted from the other satellite. It is from ESCAPE A, B, and C, and on the right side it is the anomaly of wind speed. And we can see the chlorophyll concentration. The warmer SST contributed to the development of TC, but when the TC was fully developed, the SST was impacted by TC. So actually, chlorophyll A, we couldn't see chlorophyll A concentration before TC happened, but we can see chlorophyll A concentration after TC was fully developed, and the consequence of TC on the sea surface due to the position and timing of the strong winds are congruent with the location and timing of the phytoplankton chlorophyll A blooms and SST depression due to the cooling induced of SST. And if we talk about what is the methods for analyzing satellite data, we can use multi-sensor or multi-sources satellite. First, we can downloading of data from FTP serve automatically, and we use some of sources like satellite 1, 2, 3, 4, 5, or 6. And if we use cyclone detection from near real-time data, near processing to handle lower quality of near real-time data sites. So we need to assimilate it because near real-time data is not gridded, it's not fully gridded, so we barely see how the TC form. So we have case study. This is tropical cyclone Indonesia, tropical cyclone Seroja. We use several sources of satellite. The first one is K10. K10 is from the Naval Oceanographic Office. It is SST operates satellite data only and merges level 2 SST products in the present average weight to describe the SST at a depth of 1 meter. Next, we have MWIROI. This is the remote sensing system. SST products use OI analysis, means that microwave infrared optimally interpolated. And the next we have OSTIA, the operational sea surface temperature and sea ice analysis. OSTIA system typically imported microwave data from AMSR but have limited WinSat SST imports during period gaps of using OI analysis as well. So input data are filtered to eliminate daytime observation with winds below 6 meters per second to eliminate probable examples of daytime heating. And the next we have RAM-SSA, this is Regional Australian Multi-Sensor SST Analysis. The new RAM-SSA system combines SST data from infrared and micro sensors at spin to produce SST foundation. And GAM-SSA, it is Global Australian Multi-Sensor SST Analysis. This is from the BOM produce daily SST foundation analysis at resolution of 0.25 degrees Celsius. And the last we have MUR, multi-scale ultra-high resolution, is produced by daily NASA. Unlike the other outcomes that use standard OI techniques, the MUR system uses a statistical interpolation method based on wavelength analysis,
1 minute
known as
left.
the multi-resolution variation examination. As we can see that from the RMSA, MWI or ROI is the best to describe the extreme parameters in terms for detecting tropical cyclone. And beside we have 6 satellite, we also can see the SST data from AVHRR SST level 4 products from Copernicus. So yeah, the sea surface wind in south of Timor Island before TC Seroja occurred was blowing from the east with an average speed approximately 10 meters per second. When the TC Seroja forms a tropical depression on April 3rd, 2021, the sea surface and condition are already quite strong, which is approximately 11 till 15 meters per second. And the average SST at the initial state on April 1st was 29.72 degrees Celsius. So we can see the chlorophyll A concentration as well. Compared to the initial state on April 1st, the concentration in the southern Savu Sea reached its peak on April 7, 2021, after the TC was developed. So in terms of we see the SST the sea surface wind and sea surface anomaly. Meteorological in Indonesia has a product. This is Inawif. It provides altimetry satellite to provide the data of sea surface height, sea surface wind, and sea surface wave anomaly. So the conclusion is the comparison analysis was performed by plotting the SST slope in the TC area. Based on the validation, the MWI dataset is ranked in the top 4 with the smaller RMSE. And for the observation, there is no one single satellite mission with one single sensor able to measure a wide range of different parameters. Sample at high resolution when available in situ observation and when necessary models shall be considered to fully exploit the satellite observations or complete the satellite point of view. Thank you.
Thank you very much for the presentations, Ms. Paradiva Claudia. So before we move the last presentations, I would like to request your approval to extend our meeting time about 5 minutes since we are still having one more presentations. Okay. Okay, we'll move to the last presentation by Dr. Bode Siki from Australian Bureau of Meteorology. He will bring the presentations about utilization of the satellite meteorology to support meteorological operations. Please, Dr. Bode, time is yours.
Right, so everybody can see my slide, just giving a summary of what was covered today and also my presentation coming up. Is that right?
Yes.
Yes.
Okay, and you can hear me clearly?
Yes, of course.
All right, so I'd like to cover a very short case study, an aviation turbulence event over southeastern Australia, with characteristic signature in the satellite imagery and as verified by a pilot, which occurred quite recently on the 24th of March, 2024. I have timed this session. It takes me about 13 minutes. So thank you for the extension there, Kafid, and fellow Indonesian VLab Center of Excellence staff, colleagues, and also colleagues in the audience. Right. So I just want to give you a quick summary about what happened from my perspective. First of all, I received the initial information about this case study from an operational forecaster, that's Ronnie Kumar, via email, and he provided me with some information that he extracted whilst working on the bench at the time of the event. I added to this using additional satellite images, NWP data, forecasts, and I passed it back to the forecaster. And Ronick made some suggestions for improvements, and the preliminary case study was composed. Finally, I finalized this case study for presentation at this, the Indonesian VLab Center of Excellence Regional Focus Group meeting. So maybe just to set the scene, this is if you like, the procedure that the Melbourne Aviation Forecasting Centre Hazardous Weather Unit uses to analyze, diagnose, and also do a prognosis about turbulence, significant turbulence that might involve issuing a SIGMET. And the steps that I'm going to be looking at specifically are the inspection of the satellite water vapor imagery, and also associated satellite data. I'll be looking at the LROD turbulence diagnostics. I'll show you that shortly. Then, of course, the horizontal temperature gradients, and that will lead up to the event. And then we will we'll go through that event after having done the preliminaries. So, with this slide, you should see, this is from the SIMS Tropical Cyclone Archive at the University of Wisconsin-Madison. On the left-hand side, we have the water vapor imagery with the mid to upper atmospheric motion vectors. So they are from 600 hectopascals to 100 hectopascals. And one of the things you should notice is that there is a subtropical jet over the sort of south, I guess, eastern Australia, but specifically southeastern Australia. And it also curves anticyclonically, which is a heads up that there could be potential turbulence issues with this. You'll notice too on the right-hand side, if we look at the deep layer shear, that's in excess of 100 knots. So having looked at the satellite imagery to give me the alert what's happening, next we're going to look at some NWP that if you like, that are added proof or added information that this could be a turbulence event. So first I'm looking at the LROD index. So what the LROD index is, it examines the total deformation, a stretching and shearing deformation, the vertical wind shear, and the convergence. And it's particularly quite good at picking this vertical wind shear. And so this is at flight level 340, so 34,000 feet, 250 hectopascals. And generally, if there are values greater than 30, so orange color and above, which you can see on the left-hand side image, that's a sign that there could be moderate or severe turbulence there. And you can see how nicely that fits in with where the subtropical jet is that we've had a look at in the earlier by looking at the satellite imagery. Also, they have the winds at that level, it's wind barbs, and the isotachs as these areas, these colored areas extending out from the jet. Have a look at the sounding taken at X, and you'll notice that at this level, flight level 340, there's quite pronounced vertical wind shear. So above that, at 200 hectopascals, you have over 100 knots. Below that, at 300 hectopascals, you only have 20 knots. Now, if I now step down to flight level 270, 0, so 3,500 hectopascals, again, you'll notice quite strong L-rod values in excess of 30, even in excess of 40. And again, if you look at the sounding, the same thing happens. 80 knot winds, 90 knot winds above that, and 10 knots at a different direction below that. So we now look at further supporting evidence, which is your axis G wind and temperature. And we're looking for particularly for temperature, horizontal temperature gradients in excess of about 4 degrees Celsius per 3 degrees latitude. And if we looked at that at level flight level 340, that's where the gradient is here. And again, you can see the sounding at point X. If we now go down, what we're noticing, we're now gone down to flight level 270, which is going from 250 to 350 hectopascals. That boundary has now shifted equatorward. And I'll just repeat that to make it clear. That's what it was at 250. That's what it is at 350. Now, if it's shifted equatorwards, then, or northwards in our case, this indicates that cold air has undercut warm air above, and that's a good setup for severe turbulence. So we basically have the satellite imagery, the anticyclonically curved subtropical jet. We have the values of the L-rod index, excess of 30, excess of 40 in the area, and we have the strong temperature gradients that, as we go down, move toward the equator. So as a result of that, this was essentially what was issued. This is issued at 09:03 on the 24th of March. And so you can see it's severe turbulence in the dashed area that you can see here within that red bounded region between flight level 250 and 350. And it's quite interesting to see, and hopefully you can all see the animation, what happens as we go from 09 UTC when the forecast was made through to 12 UTC. And we've zeroed on into that area where the subtropical jet is. We're looking at the water vapor imagery. And hopefully you should be able to see these little striations, these little transverse moisture and cloud features that occur at right angles to the movement of that moist air mass that moves toward BH. Can you all see that? Can you all see those little waves, transverse wave features? Maybe if I can get a response, thumbs up or not, that'll be great. Can you all see that? Okay, I'm just going to check the messages. Sorry. Okay, maybe. Can you all see the transverse banding there in the animation near where BH?
Hello, Dr. Bodo. Oh, I think Dr. Bodo have the problem of the connections. Hello, Dr. Bodo. You are mute.
Can you hear me?
Yes. Yeah.
All right. Can you see in this animation the little banding at right angles there or not? The little bands of clouds at right angles. Can you see that? It's where my cursor is, or not? Okay. All right. All right. Thank you. That's what I need. These are known as billow clouds. And so what these are, they're essentially the result of, just bear with me. Get everything out. Right. So billow clouds or cirrus clouds, they're a strong signal for clear air turbulence. The billows are an indication of the breakdown into turbulent flow in the form of Kelvin-Helmholtz instability. So that gives you an idea. Okay, now we go to the event. And so you can see it's a flight from Melbourne going through to Darwin in Northern Australia. And if you have a look down the bottom, you'll see that the blue line, which is the altitude, changes very rapidly in the region within the red rectangle down the bottom. This is from a flight radar. And so this is just some information that was provided by the operational forecaster. That was a severe turbulence SIGMET. This is, and then what appeared to happen was that at 11:48 UTC, the aircraft was cruising at flight level 320. It then encountered severe turbulence and dropped down to flight level 220, and you can see that there when it was reported. And the forecaster mentioned that the delay in reporting perhaps was being that the crew were dealing with the severe turbulence events, and when things settled down a bit, then they reported it. And you've seen the good striations, those billow clouds in the water vapor imagery, and a good case study indeed. So this is just looking at some more satellite data. In the top, you can see the banding, hopefully quite clearly there in the water vapor imagery. If we try to get a height and altitude of this, and we use the brightness temperature, you'll notice that it's actually too low. It's around -10, whereas we've seen that change in the wind direction higher up, so maybe sitting at -25, -30 degrees. And that's a hazard of looking at cloud and moisture that is slightly transparent, because it allows radiation from below to come through, and it actually makes it warmer than average. It's much more likely that these striations are at the same level as the thicker cloud that you see to the west, in which case they would be within -20 and -30 degrees. Here's an interesting cross-section, which I've taken. This is Access G cross-section from Melbourne, which is down where my cursor is, through to Darwin. And it also shows, aside from the potential temperature, but it also shows the wind at different levels, but it shows the dynamical tropopause as this double black line. You can see quite a strong folding in the tropopause, and that also as you might remember, has revealed itself as the temperature shifting gradually, strong gradients in horizontal temperature shifting toward the equator as we go down. And you can see that is also the pilots have come up against it. Oh no, they've dropped altitude to get below the area of the turbulence. My final slide, just looking ahead at what happened, you can see in the animation on the right-hand side, the development, but now we're going from 12 UTC through to 21 UTC. So in the first part of the talk, when I introduced the water vapor imagery, the Brown's index, the LROD index, that was the forecast leading up to the event from 09 to around 12 UTC. The second part was when the aeroplane encountered the turbulence, the 12 UTC, and now we're going ahead in time. And satellite imagery is useful in all of these steps, but it's also good in terms of working out what will happen in the future, where that turbulence, a signature might be detected. And you'll see that from 16 to 20 UTC, so moving after the event, the SIGMET for severe turbulence was at this location, and that's we started to see the striations there. But then later on, as we move on to 20 to 00 UTC, so into the next day, so from the 24th at 20 UTC to the 25th at 00 UTC, a lot of the striations have also moved on in the satellite imagery. So again, a number of points. Satellite imagery important in picking the feature that could be alerting the forecaster that you have a subtropical jet that's curving anticyclonically. Later you see in the animation these billow clouds developing, and I should add that there's two really good case studies in the SIMS satellite blog about that too. So Scott said you would know more about that too. And then also using the water vapor imagery afterwards, or the satellite imagery, to work out the progression and to keep monitoring this feature. Thank you.
Thank you very much for the presentations, Dr. Budeseke. So we will move the question and answer sessions. If you have the questions, you can type in the chat box or raise your hands. We have 5 minutes for the questions, please, for all participants. Okay, Agus Nur. Okay, you can open the mic.
Okay, thank you, Mas Hafid and everyone, the speakers. I want to ask to maybe to Hanif and Farah. It's related to the tropical cyclone. The first one is for Hanif. First, I have two questions. Mostly the system that developed in Indonesia in the early stage of tropical cyclone, or even it's still in the stage of tropical low or tropical depression. And we in the forecaster side, sometimes we have difficulties to find the low level circulation center, or maybe center of the system to start the step one of the forecast analysis. And my question is, and sometimes we find difficulties to use only animation, the visible data, or maybe the infrared. So I have question to Hanif. In your division, is there any derivative products of your satellite data that can help us to find low level circulation center? Because at the moment we usually use the data from another institution like NRL, Ramsira, GTWC, and it would be great if we have the data in our agency. And the second one is related to the machine learning model. Do you have in your division any plan to develop a machine learning model on satellite data to determine the TC intensity? Because this is important for us in the operational. This is to compare the result of the machine learning model with the forecast analysis that we usually do manually by the forecaster, which is very subjective. Okay, and the second one for Farah. We know that in the area of Indonesia, mostly we have one SST, which is favorable with the development of tropical cyclone. And we know that not only SST factor that help the development of the TC. So is there any particular tips for your side to see the specific SST that can help us to help us to define the development of TC genesis. And the second one is about the chlorophyll things. In your presentation, there is a development of chlorophyll, which is in the same site with the development of tropical cyclone. Which is the first one to develop? Is it the TC develop and then the chlorophyll develop, or the chlorophyll develop and then TC is developed? Okay, thank you.
So please, Mr. Hanif, you can answer it. The first.
Okay, thank you, Mr. Hafid. Thank you, Mas Agus, for your question. Interesting questions, actually. I would like to answer the first one. So actually, we currently don't have that kind of product, but in the future we will plan to develop that. So hopefully we can provide you the notification whether there is an early stage of tropical cyclones such as tropical low, etc. We hope we can develop it in the near future. And then the second one, we also have the plan to develop the machine learning model implemented into the advanced forecast technique in the future also. But since there's a limitation in human resource which can develop that kind of thing, I believe we couldn't have that innovation this year, but hopefully in the near future, maybe next year or next 2 years, we hope.
So, Mrs. Farah, you can answer that.
Okay, let me answer about the SST things. How to see the SST to detect of tropical cyclone, right? I think SST as the definition of tropical cyclone and the formation of tropical cyclone genesis, the SST must be at least 27 degrees Celsius or above 26 degrees Celsius. Below 26 degrees Celsius, actually, the storm wouldn't develop. But we couldn't only see the SST because we also see the sea surface wind. In the sea surface wind, we can see like the rotation or eddy form in the tropical cyclone or pre-tropical cyclone. So we can see that if the SST above 26 degrees Celsius and if the sea surface wind like forming the eddy or the rotation, it means that, oh, it must be pre-tropical cyclone. And for the chlorophyll A concentration, chlorophyll A concentration happened if upwelling occurred. And upwelling occurred in response to the tropical cyclone. It is happened after tropical cyclone was developed. So after tropical cyclone was developed, or maybe like after the mature stage, it drives the ocean drift like the SST inducing cooling SST, and it 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 drives the upwelling. So that's why the chlorophyll A concentration appear in the sea surface. Yeah, thank you.
Okay, thank you, Mrs. Farah. So we will next question for Dr. Bodesike from Mr. Richards. Can you show in the chat box, Dr. Bode?
Right. Sorry, the actual chat is very temperamental. When I've noticed Richard's presentation, the question, but I can't. When I get to it, suddenly it flicks around. So could you just read it out, because I may have a response as well.
Okay. Mr. Richards, have a question for you about the turbulence. It is possible for turbulence like that happens in equator place, like in Indonesia, from your presentations.
Okay, so the turbulence that I was the case study I provided was to do with turbulence associated with the subtropical jet. The subtropical jet typically doesn't really, because Indonesia is very equatorial, it's going to have minimal impact on directly in this fashion on Indonesia. However, you still get atmospheric shear occurring in Indonesia, and that may have associated turbulence. And I've actually got a nice little example, little animation that I wanted to show you. That's why I was so busy. I wasn't paying attention to the screen. I was trying to answer Richard's question. So I'm just going to share my screen with your permission, and then I'll run an animation, and hopefully you can see the animation. Here we go. Let's see. Can you see I'm going to animate that. This is a squall line near Singapore. So it's it's in the South China Sea and Indonesian islands around. If you look at the red ellipses, you should be able to see the transverse kind of banding in the clouds. Can you all see that or not? So you can get similar features that might have developed due to strong shear across, for example, an inversion, but they're unlikely to be associated with the subtropical jet because that's too far poleward in the normal position to where Indonesia is located. Thank you.
Yeah, thank you very much, Dr. Bodo. So we move in the end of the sessions because the limited time. So other question you can dial it to the speakers. So before the closings, I think Bu Ani has announcement. So please, Bu Ani.
Yes, thank you very much, Pak Hafid, and all the speakers for presenting today and for moderating today's sessions. I just would like to have one very important information that for the next regional focus group meeting, it will be hosted by the BOM. So I would like to encourage all of you to join that interesting session so that we could have another discussion with everyone again in next session. So thank you once again. Only that. Thank you.
Thank you, Bu Annie, for your announcement. So I would like to say thank you to all the presenters for the quiz presentation and to the participations for their active participations. Thank you for your attention and have a great day. See you in the RFG June. Bye-bye.
Okay, thank you. Thank you,
great
Annie.
Thank you,
day
Dr.
all.
Pado.
Thank you,
Thank you,
Kaffi.
Mr.
Bye.
Richard.
Thank you, everyone.
Pak Hafid, can we copy all the chat here so that we could follow up the unanswered question and then we can share to all participants here?
Okay, I can. Sorry. Sorry, Bonnie.
Yeah, could we save the chat so that we could have all the question and answer,
Yes.
and
Yes.
we can request all the presenters to answer the unanswered questions, and then we can share that to all the participants after that.
Yes, I will list in the word.
Okay, thank you.
Thank you.
Thank you, everyone. Have a good day all. Bu Kapus, terima kasih banyak Ibu.
Terima kasih Mbak Ani.
Sama-sama Bapak Ibu semua.